remotely sensed data. We've built a reputation as a leader in the hyperspectral analysis space, and our ENVI products focus in on bringing in hyperspectral,
versatile, and it can be used across a wide variety of applications. So anything from hazard monitoring and disaster response, oceanographic monitoring for ship detection or oil spills, to biomass estimations or change detection. And we'll show you a few examples of these types of applications later today, but first we'll go over a little more about SAR data and the initial processing steps to get your data ready for analysis. So one of the fundamental properties of any SAR instrument is the band frequency. This is the frequency of the signal that is emitted from the instrument itself. And SAR instruments can utilize a wide range of band frequencies, seen here on the left. They go from the low frequency P-band SAR up to high frequency X and K-band SAR. The most commonly used frequencies are highlighted here in red. Those are L, C, and X. They tend to be very common. And band frequency determines a number of important things about how the data can be used. For example, longer wavelengths or lower frequency SAR signals penetrate deeper into materials such as vegetation or soil, as you can see here in the upper right-hand corner. So if you wanted to look at a forest floor that lies below a thick canopy of vegetation, you would need L or P band SAR data. If you're trying to use X or C band data, you're just going to be imaging the top of the canopy and you can't see through it to the forest floor. In addition to penetration depth, the band frequency also determines the size of features that your SAR data is sensitive to. We have an example of this on the bottom right-hand corner here with the tree. And waves interact with features that are similar in size to the waves themselves. So high frequency X or K band SAR has a very small wavelength, and those essentially see materials of similar scale, like the leaves on the trees, as you can see here in the bottom right. Lower frequency L and P band SAR have longer wavelengths, and they interact with larger features like the tree trunks themselves and large branches. So the key here is to have an idea of what you're looking at in your work before you go getting any data, and to make sure that the band is appropriate for what you're trying to do. X and C band SAR are the most commonly used for general surface imaging, while these lower frequency S, L, and P bands are more appropriate for things like biomass studies. So even though SAR is growing in popularity today, this technology has been around for several decades, as you can see here. There's a long list of active SAR satellites today, and there are many more planned for launch and operation in the next few years, which we are all extremely excited about. There's a mixture of both free and commercially available data in these satellites. So the European Space Agency's Sentinel-1 data is freely available at approximately 15 to 20 meter spatial resolution, is very common, while the higher resolution data, such as TerraSAR-X, is not free. There are advantages to both datasets depending on your study and your goals. So while the high spatial resolution of paid data might be the key factor for some people, others may find the global coverage and the 6 to 12 day revisit rate of Sentinel-1 more useful for their application. And narrowing in on the question you're trying to answer will help you determine which data type is the best fit for you and your work. And now I'll turn it back over to Nigel. He has another poll question for you.
Great, thank you. I'm just looking at that chart. We're obviously very excited to see the launch of new SAR constellations, the likes of Capella, Express SAR, ISI, and to come with Umbra Labs. It's a very interesting time because those revisit rates that we get from Sentinel of 6 to 12 days, depending on where in the world you're studying, potentially will come down to 6 to 12 hours, and as the constellations build, the revisit rates can be as good as hourly. So the promise of future data is very exciting at this time. So let's take a look at the next poll question. And that should be on your screen now. And if you'd like to take a look at it here, we're really trying to understand what's holding you back from using SAR data. Is it the data availability, the ability to process it, the storage requirements, the complexity, or indeed the cost of SAR data commercially? So we'll give it a couple of seconds and we'll close the poll down. I'm seeing some good results here. Excellent. So you should see the results on your screen. Again, another multiple option poll there. And obviously processing and complexity, two of the biggest there. And we're hoping here with the webinar series that we're running, we'll demystify some of the complexities, show you how to develop and produce easy to use workflows and deploy those for colleagues or for operational systems. So I think SARscape has a lot to offer to help reduce the complexities and to improve the processing capabilities. And obviously data availability, I think that will continue to improve. Cost of SAR data, the more I'm sure the market will determine what's going to happen with pricing there, but one would think with the availability of more and more data that we would expect the price of SAR data to come down as well. So thank you, that's excellent input to that. We'll move on to the next slide.
So speaking of processing, before we get into some specific examples of how you can use SAR in your work, we'll talk a little bit about the initial data processing that you may need to do. So when you're working with SARscape and ENVI, you'll find all the tools you need in the ENVI toolbox. Here on the right, we have a little screenshot of SARscape in the ENVI toolbox. And common data processing steps that you'll need to do are importing your data, of course, multi-looking. If you're working with multiple scenes, you need to co-register your data. And you also need to filter and then geocode and radiometrically calibrate your data. All of these are initial processing steps that you need to do before you can really get into any deep analyses. You can also use SARscape in the new ENVI modeler. I am a big fan of this. All of the SARscape tasks are available in the modeler, and you can chain them together to automate or batch process your data. So here we have an example of a simple data pre-processing chain that takes it from a newly imported scene all the way through to geocoded and radiometrically calibrated data that is ready to use. And your models can be simple like this one, or they can be as complex as you want. And later we'll show you an example of a data fusion model using both Sentinel-1 SAR and Sentinel-2 optical data that was built in the ENVI modeler. So let's take a quick look at each of these processing steps to get a sense of what they're doing. On the bottom here, we have an example ENVI modeler processing chain, so you can see where you are in the process as we go along. The first step in any analysis is to import your data. You can't do much if you haven't imported it. So during your import step, you can subset your scene using a region of interest shapefile, or now in the new SARscape, you can also use a KML or a KMZ file. And this helps cut down on your data storage and to make your processing run much faster, since SAR scenes can be very large. During that import step, you can also choose the polarizations you want, and this will depend on what you're doing with the data. We'll talk more about this in future webinars. Today, we're just going to cover applications. So you can also mosaic scenes from the same track, and that will simplify your data processing. After you've imported your data, multi-looking is your first step in removing the noise, or we call it the speckle when we're talking about SAR data. And this process combines and averages the intensity values within a set number of pixels. So it gets rid of that salt and pepper look that you see in the imported Sentinel-1 data on the left here. Multi-looking both removes some of the noise and it creates square pixels rather than these long squashed rectangular pixels that you have after importing your data. And those long rectangular pixels are due to the look angle of the satellite. Since it's not looking straight down, it's actually looking to the side. Everything gets a little stretched out. So multi-looking fixes this. Co-registration is a necessary step when you're working with multiple images. For example, if you're doing a time series analysis, this is a critical step in your data processing. Co-registration makes sure that the footprint of one pixel is the same from one scene to the next. So you can actually compare the data within each pixel and know that you're comparing the data for the same spot on the ground at all times. If you don't do this step, the pixels might not be covering the same feature and your analyses may not work, or they may produce results that aren't actually accurate. Filtering is your last noise reducing step, and this can be done a number of different ways depending on your data and what you're trying to do. If you're working with 3 or more scenes over the same area, so something like that multi-temporal analysis, de Grande despeckling is often the best method to use because it takes into account the temporal aspect and it keeps features that are persistent and removes ones that are not. If you're working with only 1 or 2 scenes, then there's also single image filtering, which is often the best option for this case. So here on the bottom right, we have an example of before and after filtering. The image on the left has not been filtered and the image on the right has. And you can see that salt and pepper look to the data has been removed. The last step in your data processing before you get into any kind of analyses is geocoding and radiometric calibration. And this step applies a geographic projection to your scene, so it actually looks like something recognizable that you would see if you were flying over the area. And this step also calibrates and normalizes your intensity data so that you can now make actual meaningful comparisons from one scene to the next. Without this step, your intensity values are not comparable from one scene to another, so it's a very important thing to do if you want to actually look at how the intensity changes. Once you've completed these initial data processing steps, you can do a huge variety of analyses using your data. For example, this data that I've been showing you here was used to create a flood map of the Wilmington, North Carolina area after Hurricane Florence made landfall on the east coast of the US this September. And now I'll turn it over to Megan.
Thank you, Sarah. So we've been following a simpler example of what is possible on the modeler. And I think one of the most important things to bring up about the modeler is once you have a model set up, you can have whatever inputs you want in it, such as if you run it through a scene on one particular date, all you have to do is when you run it again is change your inputs and it'll run through the model all by itself. And so the modeler also allows for much more time-intensive processing. For example, this ENVI task that's up on the screen right now, this ENVI task does is it actually does full pre-processing of Sentinel-1 and Sentinel-2 data to have a data fusion result at the end. What I mean by this is in the blue that starts at the bottom left-hand corner. We have full pre-processing from subsetting our raster to an area of interest, going through all of the bands, radiometrically correcting them, and then atmospherically correcting them as well for all of the Sentinel-2 10, 20, and 60-meter optical imagery bands. Now, on the top part of the screen that's highlighted in red, we actually have all of the pre-processing, some of it which should look a bit familiar now, for the Sentinel-1 SAR data. And so this goes through all the pre-processing steps, and then it goes and we can actually combine these two different data sets, the Sentinel-2 optical imagery with the Sentinel-1 SAR data, to create a band stack or a data fusion product as our end result. So we have an image on the right, and what this is showing is the Skaneateles Lake in New York, which is the large lake in the middle. And looking at this image, it is an RGB image, where red is the red optical band, or the red band from Sentinel-2. Green is the green band from Sentinel-2. But the very bright blue color we see is actually the SAR band of vertical-vertical. And what this is doing is really highlighting the vegetation in this region. As we heard that Sentinel-1 is very sensitive to these surface characteristics. And so when we're looking at this combination of data, we can more easily actually pull out the difference between the very green agricultural fields and the very green forest. And it does an amazing job with further classification techniques. And with that, I'm going to hand it back over to Nigel for the last poll question.
Great, thank you, Megan. Yeah, so the fourth poll question will be coming up. Should be on your screen now. And here we're looking to understand, what your main area of interest is, what application you're looking to apply SAR data to. And the options are activity monitoring, land surface deformation, natural hazards, agricultural forestry, or maybe you have some other. And obviously those that other, we'd be interested to find out more later from you what those are. And as we're getting ready to close that poll, one of the things I'm interested in is making sure that you are aware if you have questions, you can put those into the questions box, and we'll try and get to those at the end of the webinar. Okay, looks like we have some results, and probably the highest one there you see agriculture and forestry. I think we're going to cover a little bit on that later on this one. Land surface deformation at 19% and natural hazards at 22%, also very popular. And then good to see a lot of other applications, so we look forward to exploring those with you too. So thank you for your participation here. And now if you can think about some questions as they come up at the end, and we'll hand back to Megan. Thank you.
All right, so thank you so much for telling us about, your interest of applications, and luckily we are actually going to go over a few of these today. And if we don't hit them today, we're most likely going to go over them in one of our future webinars. So as you can see, there are many different SAR applications, and the ones people usually think about are looking at earthquakes and DEM generation, or techniques that use something called interferometry. And so we're going to hit on one of those today, which is the DEM or DSM generation, but we're also going to be talking about deforestation, flooding, and activity monitoring. And so jumping right in, digital elevation models or digital surface models are one of the most classic uses of SAR data. How this works is you have a pair of images, and these images, almost very similar to optical photogrammetry, will be looking at the same spot, and if they're from different view angles and from different time periods, you can actually get higher resolution information, such as topography or displacement that's occurred between the two scenes. So on the screen, on the left-hand side, we have two SAR images, and in the middle of the screen, we have a workflow that creates a DEM using that pair of imagery. And on the right-hand side of the screen, we have these outputs. What's really amazing about this system and interferometry in general is it actually uses the phase, as we saw in the beginning, to get these high resolution changes between these images, such that even if your satellite has a lower resolution, you're still able to get millimeter to centimeters of change or displacement or topography using those satellites because of how precise the calculations for the phase and using these techniques in interferometry work. And that being said, however, the best DEM results do come from higher resolution SAR imagery. Now, when we're speaking of interferometry, we tend to focus on terrain and infrastructure monitoring. On the top left-hand side of the screen, we have a displacement map. And what that is showing us is the changes that are occurring on a ground level between two separate images that are separated by time. And in this case, this is from before and after an earthquake has occurred. And we can see that there are these large areas of displacement that occur along a fault line that's going through diagonally, that image on the top left-hand corner. And so using interferometry to track displacement, we can find areas where there might be possible hazards or areas of interest that you might want to look out for that are happening after events such as an earthquake or a landslide or subsidence. In the bottom left-hand corner, we have a DEM, and this is when two SAR images have a change in how they're looking or their looking geometry at a specific scene. And we can get these high-resolution DEMs that allow us to get these centimeter and millimeter topographic changes. And the great thing about using interferometry to get DEMs is you can actually use that DEM for other SAR processing, especially with how high of resolution you can get. Now, on the right-hand side of the screen, we actually have some multi-temporal analysis as well. This is meaning more than just a pair of SAR scenes are used. In the top right-hand corner, we have the displacement that's happening over a region over time. And what this allows us to do is actually get much higher accuracy. As we're processing more and more scenes, we're able to get rid of noise such as atmospheric effects, and you can track when these major displacements begin to occur. And so as you can see in the top left-hand corner of that figure, we're able to track these specific pixels over time and see when this displacement is very much beginning to happen, especially with that green and yellow line at the very top where there's a sudden downturn. Now, in the bottom right-hand corner is something called coherence change detection. What this does is it takes a pair of images and it checks the coherence between the two. So what the coherence is how similar these scenes are, meaning that if they're very similar, they will have high coherence, and that means not much has changed in between them. And if they're very different, such as something has occurred between one scene and the next, they will have very low coherence. This example in particular is from before and after the Christchurch earthquake in New Zealand. And the areas in red have very low coherence, which is actually due to liquefaction that occurred in the city, causing quite a bit of infrastructure destruction. Now, we're going to jump from terrain and infrastructure monitoring to something that seems to be of interest for quite a few of you, which is looking into forestry, or in this case, deforestation. So first, jumping into what this image is on the screen, is those areas in pink are where there's a high coefficient of variation, meaning that these are areas where a lot of change has occurred. And in this case, unfortunately, those are areas where we've gone from having highly forested regions to not very forested at all. One of the tricks that comes into play when you're looking at deforestation with optical data is a lot of the time this deforestation occurs during the rainy season, because people are aware that there are satellites and aerial imagery that can be used to find this deforestation and hopefully stop it before it can spread. And during the rainy season, because of the cloud cover, we are unable to get the proper kind of imagery to keep track of what's going on at a good temporal scale, which, as we heard previously, being able to see through clouds is one of the SAR's great capabilities here. When deforestation begins to occur, especially in this case in the Amazon, what happens first is there usually is a long, thin road cut out that is actually an airstrip. From that, new roads spread from that region, and then the deforestation and cutting actually begin. So using timely SAR data, we can hopefully catch this just as the airstrip and roads are begin to be cut, and stop the deforestation before it even starts. So on the left-hand side of the screen, we have an image of all of the deforestation that occurred in that bright purple color. But what's really interesting is if we actually look on the right-hand side of the screen, we've actually split up the deforestation to different temporal periods, meaning in between the two satellite SAR scenes that we have. And in this case, you can see a lot of this is a very bright green color, which falls between November and January, which is the peak of the rainy season, meaning that most of this deforestation that occurred would be almost invisible to optical data. And the great thing about SAR as well in this case is it's very sensitive to surface changes, meaning that we're able to catch these changes as it goes from this highly vegetated cover to very little cover at all. Continuing on the sort of path of looking at clouds, we're actually going to go back to what Sarah was talking about previously, and that's using SAR for flood mapping and disaster management. Here is some images from the Hurricane Florence that occurred in the United States this year. And we can see that there's a lot of standing water on the roads. So water has a very particular response in SAR data that makes it very easy to pick up. So when we're trying to map through these clouds and get an understanding of the flood map, we're able to do this with SAR and get these responses that we can send to first responders and make sure that these areas that are flooded can be properly either have people come in or we know in the future where these hazards might exist. Here we have some pre-storm SAR data. On the left-hand side, we have Wilmington, North Carolina, and on the right-hand side, we have Goldsboro, North Carolina. And we can see that there is a river running through the middle, the Wilmington one, with this much darker color. Now, if we go into some post-storm SAR data, we can see there's much more of this dark reflectance response, especially in the Goldsboro scene. And so we're able to detect this water much easier. Lastly, you can do multiple different ways to actually get maps and understanding of this flood change that's occurred. On the left-hand side of the scene, the purple, pink, and blue show areas of inundation where water was not previously. And this is something created using a dual colorimetric RGB, where red and green are singular bands of the post-flood, and then the blue band was actually the average pre-flood, and we're able to see these changes in between the post and pre-flood and really highlight those areas where this water is now standing in areas where it wasn't previously. And on the right-hand side of the screen, those red areas highlight the flooded areas that are new to the scene. And this is done using thresholds and ratio calculations all in ENVI and SARscape. Now we can overlay these maps with LiDAR building data and pinpoint areas of interest for possible emergency response. Now, going on to a bit more of a fun example, we're going to look at some activity monitoring. So activity monitoring is a great way to detect changes that are happening with construction, demolition, especially in urban areas. What this means is because SAR is so sensitive to these surface structures and surface changes, we're able to detect when these changes occur and get a view on what's actually happening on the ground surface. In this case, coherent change detection was done over Burning Man, a festival that takes place in Nevada in the United States, where there are over 70,000 people who all join together and camp out in the desert for a week. On the right-hand side, we see this image, and the bright blue areas are areas where there has been large change in between our pre-Burning Man image, which happened in June, and an image actually taken during the event, which is in August. So that bright blue ring you see is tens of thousands of tents and vehicles that are all parked and camped up and set up for this event. And if you look very carefully at the scene, you can also see dark blue lines that are etched into the surface of the desert. And this is actually where tracks from trucks and cars have gone over these areas multiple times, actually creating some deformation in the surface. And with that, I'm going to hand it back over to Nigel.
Great. Thank you very much, Megan. Well, this does bring us to the end of this first webinar, and we'd love to open it up to questions. So if you would like to put questions into the questions box, we will start working on those and get some of them answered for you. I know certainly initially some people were asking about whether or not the webinar would be available and the slides be available. You may have joined a little late. So we will be making all of these slides available to you as a PDF and sending you a link to the recording of this webinar. And you should receive that email in the next 2 business days. So thank you for that question. And then we have one from David, who is relatively new to SAR, saying for someone who doesn't know SAR, how easy is it to get started? I think, Megan, that would be a good question for you, as you're just entering your 3rd month here with us, so you probably have great experience on getting up to speed.
Absolutely. I think definitely one of the most important things about first getting started with SAR is understanding what you need from it. Because SAR, like any other platform, it hits some very specific niches. So knowing what you need from SAR, or that your application really needs synthetic aperture radar, is the first step to understanding, getting started with it. Now, from that, and especially with the fact that I just started here as well, how easy it is to get started with SAR, it really depends on, of course, what you want to do with it. But the great thing is that a lot of the time, especially with SARscape that I found, is there are a lot of workflows and tutorials, and we actually have a great tech team that'll help respond to any questions. So even though there might be some complexities in some of the math and responses, getting started with SAR in this case wasn't actually that bad at all, just because I had a lot of resources that are also available to all of you guys when you have SARscape.
Great, thank you. Sarah, let's get a question for you here. We've got Giancarlo asking, I'm not a programmer. What can I do with just the modeler?
Well, I am not a programmer either. I'm working on becoming a programmer. So this is actually something that I did myself. I think the modeler is a fantastic way to play around with your data and see all the interesting things that you can do without actually needing any programming skills. So the modeler has all of the same SARscape tasks available in the ENVI modeler has all the same SARscape tasks available as the ones that you would see in the ENVI toolbox. But in the modeler, you can drag and drop and connect various tasks and create these automated workflows, do batch processing. So it really opens up a whole other level of possibilities for your analyses rather than having to sit there and do them manually. The one thing with the modeler is to be really aware of where, like, the flow of your data going through it. So it's something that helps you be very aware of what you're doing to your data at any given step. And it's an excellent way to get into these potentially more complex analyses without actually needing programming skills.
Great, thank you. And then Sabrina has a question. She's interested to know whether we'll be notifying folks with the next webinars. Yes, the next one will have a note on it on our final slide, but we also will send out email invitations to all attendees of this one. So, glad you've enjoyed the first webinar. Philip is asking about PSI. Can you speak about PSI?
Yeah, there have been quite a few questions about, I'm assuming by PSI you mean the persistent scatterers.
Right.
So we've had quite a few questions about persistent scatterers, and it's a really interesting analysis that you can do. So there's two different things that you can do in terms of temporal stacking and looking at really fine deformation. One of them is persistent scatterers, or PS, and the other one is SBAS, or small baseline subset. And they are used in different situations. So persistent scatterers is really great in urban areas where you have a lot of stable reflectors, so things like buildings that aren't changing from one time to the next. SBAS is something that's really good for these more diffuse things where maybe you have more things changing and you want to look at the overall deformation in a region rather than points. So persistent scatterers works by finding the pixels in your scenes that are coherent, or that means they don't change that much from one time to the next. And then it drops out everything else. So all the stuff that isn't coherent is removed. And it just looks at all of these coherent pixels and looks at how the phase changes from one time to the next. And this actually brings me to one other question that someone else had, was what is the finest deformation scale that you can actually identify? Using persistent scatterers and SBAS, you can do anything on the order of about 3 to 4 millimeters of deformation per year. So you can get some really fine motions resolved using these SAR feeds.
Great.
If I could also say with that, I'm not quite sure if you brought this up, but our persistent scatterers now also has an incremental mode, which is absolutely fantastic.
Yeah.
What this means is if you are trying to stay constantly up to date with an area of interest, and you've run all of your SAR data previously, perhaps for the past 3 years in some cases, just tracking changes, now when you have a new scene that comes in, it is just added to the pile. So it's just added to the stack of images that you have. So instead of having to rerun all of your old data and do a lot of processing time, this one scene is just added in, and in this case, added to the plot and the baseline, and you're able to go through the processing much quicker. And this is something that I'm extremely excited about.
Mm-hmm. Me too.
Great. Then we have a nice comment from Nangula. He's just saying, great, so good to be here. I hope to learn as much for myself and my students. So wonderful to hear that you're teaching SAR and SAR analysis within your institution there. Thank you. A good question from Stephanie. Nice to see some interest here in the burn map in California. And the question is, what SAR platform was used to look at that information?
Absolutely. So that was actually Sentinel-1, because one of the great things about Sentinel-1 is the fact that it's really great at seeing these small changes that occur. It's pretty much a platform that was made for displacement. So for that fire map and for another fire map that I created for the Woolsey fire, the Sentinel-1 data was able to pick up those changes that were occurring from going from highly forested and urban regions to much more barren areas of interest.
Great. And then we have a question from Emal Rumi. What is the finest change in topography changes that can be detected with SAR?
So that one is what we were just talking about with the persistent scatterers or the small baseline subset. You can resolve
after this webinar as well. So please, if you're interested. To wrap up the